All right, well, hello. So we have kind of a long list of topics, but each of them are relatively short today. So um, I'll review some points about, sorry. Just wanted to make mention of homework 10, that this is on inductance. And you can be turning this in at the very beginning of the break if you'd like, or if you want my feedback earlier for practice purposes, you're most welcome to email it to me and I'll give you feedback. Homework 12, notice that there's no homework 11. I should write that here. No homework 11. I made a judicious choice to skip a little bit more detailed exploration of circuits. If you would just like a copy of that just to see what it is, or just try it on your own, say you wanted to get a little bit more practice with inductors and capacitors and circuits, I don't want to hold you back, so let me know. I can share that with you. Also, when we come back from the break, we'll do a little bit more sort of I guess you could call it kind of medium qualitative. We're not getting super deep into the ordinary differential equations, but what we are is trying to do some sense making around these complex impedances. We'll do that when we get back on Monday after a spring break. So homework 12 is going to be just a warm-up for thinking about the notation of waves. That'll be due after our exam. I should also mention that our exam number 3 will be on Friday the 7th. I think that we've talked all about what kinds of things to expect, Faraday's law especially, inductance, and then also this magnetization M, H, and B. Those are some things to be expecting. We'll talk more about that when we get back. The solutions are now posted up online up through homework 9, and on Friday I'll have posted the solutions for the inductance assignment. I would like to recap a topic that came up about how energy is stored in capacitors and inductors. We'll get to that in a moment. I'm going to review a few points about homework number 9, some things that I felt like maybe I overlooked and some things that were commonly missed. Then I want to get to the meat of some new material today, which is looking at Ampere's law and looking at it revisited. There's kind of a strange dilemma that we're going to come across that maybe it doesn't appear obvious how to solve it, but it's actually going to be our way into understanding about electromagnetic waves. It's a very important point, and it's going to lead to our last modification of Maxwell's equations. It's really exciting. So modification of Maxwell's equation. And then that'll be it. I'll also briefly show a Python notebook that I created for exploring and understanding wave notation and just sort of like building an intuition from it. And then we'll talk about kind of where we're heading here for the rest of the semester. So that's sort of what we have planned for today. I know it seems like kind of a lot, but it's actually going to be going by pretty fast. I just wanted to maybe open with just a few discussion points about the homework number 9. So many of you right away got that for this, I'll just bring the problem here. You've got this sliding bar and it's moving to one side, and you could see very clearly that the amount of area this time is changing, and so flux is sort of B dot dA. This can be simplified in this case as just a B times A, and if we're trying to get phi dot, then of course we can write this as B A dot plus A times B dot, where A is just the area, right? And so in this case, this is the part that actually matters. Most of you were able to work through everything except for there was a little bit of confusion around how to deal with this part D here. So for part D, assuming that it starts it starts with some speed v naught here, we can write out an equation of motion using F equals to ma. And so the way to go forward here is to say, well, m, that's dv by dt, and you can set that equal to the force that's going to be especially on this part 1 here, which is our ILB force, right? So ILB with a minus sign. And that current here, it depends on the velocity. And so we end up with an expression where we have v dot is equal to minus some constant times v. And this is a separable first order differential equation. So just to remind you that you can rewrite that as dv divided by v is equal to minus that constant times dt. You can integrate both sides, and I'll let you take a look at the solutions to find out more. For the loop that's dropping in the magnetic field, so one thing is that we had to think about first what's the condition for our terminal speed. So some of you wrote that it's dv by dt is equal to 0. That's excellent. And so remember that mass times acceleration is equal to the sum of forces. And so if you wrote that the sum of forces is 0, that's great. If you wrote that the dv by dt is 0, that's also great. Those are the conditions that the velocity is not changing. Could still be a constant, right? And so that's the situation here. And let's see here. I'm just going to quickly overview because the solution is written clearly. I think hopefully it's clearly. If it's not clear, just let me know and I'll try to help clarify more. But so we basically have the sum of forces here, which is going to be that's going to be our EMF, so it's ILB, so E over R, that's our EMF over R is the current times LB, and that's going to be minus mg. And so that's the sum is equal to 0. From that, you can figure out about an expression for the terminal velocity. What else? I just wanted to maybe make some comment then that if you solve for your net force in part C to try to write a differential equation for our the speed of the loop, we're going to be taking a look at that sum of forces, so mg minus ILB. And we're going to set that equal to my double dot, right? So this is before we sort of get to this like terminal velocity. And of course, we're going to use for this I here, we'll use BLV divided by R, right? So, and R is related to the resistivity. And if you work that out, it's the resistivity times WTL, but then there's 4 of these bars here. You can do the same thing for the mass. This ends up being a differential equation in V because y dot is equal to V. So that means that y double dot is going to be equal to V dot. So you can rewrite it like that. That ends up getting you a differential equation. One of the things that I wanted for you to do is to figure out a characteristic time. One of the things that I like to do is that whenever I see something where it's like an e to the minus t times some stuff, I try to rewrite it as like an e to the minus t like divided by the stuff, right? Or try to re-massage it into that. And then that stuff becomes a tau. And so then whenever you see an exponential function like that, where it sort of decays, right? So it decays like this. That means that according to if time is 0, then you have some value. And when time is, say, equal to tau, then you end up having 1 over e, which is about, what, 37% or so. So this is what is called as a characteristic time. And in this particular situation here, the velocity is actually increasing, but it's doing it with this sort of exponential function. So it ends up looking like a function like this, where the speed increases up to some terminal velocity. So this is the speed as a function of time when you solve this differential equation. So you end up getting some v of t is equal to g times tau, 1 minus e to the minus t over tau, and that tau is equal to mr over b squared L squared, or if you fill in for what is it, this rm and r, so this sort of mass density and then also the resistivity, right? They both kind of sound similar. You'll end up with 16 rm r over b squared. One of the things that I had forgotten to do when I asked you to solve the problem for aluminum is I forgot to specify the value of a magnetic field. Of course, that would be important. I overlooked that. My apologies. Some of you actually just wrote, okay, well, what if B is 1 Tesla? Or what if, in my example, I said, well, what if B is a fifth of a Tesla or 0.2 Tesla? So it doesn't really matter. If you try plugging in some values in here and some value for the magnetic field, which is what you'd need. For a 0.2 Tesla field, I plugged in all these numbers here. For aluminum, I wrote down the numbers in my solutions. You can find out what these two numbers are here by looking them up, or I supplied this for you. I got something about 30 milliseconds for 0.2 Tesla. So for one of you, you chose 1 Tesla, so that would be 5 times as much, so that'd be 25 times less. So I would be talking about 30 divided by 25, so approximately 1 millisecond for 1 Tesla field. That would be what I would roughly guess. So that's just me sort of thinking on the spot, just to kind of help to sort of think through some of that here. So in other words, a bigger field apparently means that the time scale of reaching terminal velocity is much faster, which I guess kind of makes sense because the magnetic field then has more of an effect, right? Okay, so then lastly then for the AC generator, this was a good one, I think, because it's really helping us to make some sense of things. And actually, I'm going to just move to a better picture of an AC generator here. It's this picture here. Let's see if I can make it a little bigger. It's not. Okay. All right, I'm just gonna use this picture here. I don't know, I wanted to make it a little bit bigger, but that's okay. So you can see here that this picture is supposed to show you that the wires here can make contact. The right-hand side wire in this case makes contact with this first sort of collet, like a circle, but it's always in contact with it. And then the left-hand side is always making contact with the back one, but it's not making contact with the first one. You can imagine maybe there's some enamel around this little area right here to keeps it from contacting that. So I realized maybe it wasn't totally perfect to understand that from the picture, but nonetheless you can see that when this loop is perpendicular, you're getting the most amount of flux, and when it's like faced up down, you're getting no flux going through. So hopefully you can see that there's a cosine type of relationship there. And maybe I will also just sort of draw this picture here that if here's my magnetic field and the loop is doing something like this, is just kind of like a 2D picture here, then the area is pointed this way here. So the area vector is pointed this way, the magnetic field vector is pointed this way. This is sort of just like a side view. You could imagine that that there's going to be sort of a cosine relationship, right? So in other words, the flux that's going through this loop is the magnetic field times the area of this loop, but also times the cosine, right? Now, some of you are also like, well, cosine of what, right? And so this is a point where this is going to help to actually bridge to our discussion about waves, which is also related to our discussion of phasors in our circuit analysis. So I like to think of it like this, that if you get up to some particular time, then you've sort of reset. And so because cosine repeats itself over a 2 pi time scale, we're going to throw in a 2 pi in there. That 2 pi over t we call as omega. It's just a convenience factor. It's basically saying that I can rewrite this as b times a times the cosine of omega t. So hopefully that helps dispel some of the mystery of why it's written like that with this omega. We'll see another thing similar, but in space, when we actually start talking about waves. But I wanted to mention that here, that this cosine of omega t. And you're asked to also make a connection between the amount of the amount of power in terms of this electrical power, which would be, okay, you could call it as like I squared R, right? That's the amount of power that would be dissipated. Or we could also say is E squared over R, right? So this is the EMF. Or we can think about looking at it from a torque point of view. Now, something that I completely neglected to mention, but I felt like after I really thought about it, I realized that it's not as trivial as I thought it was. In fact, I looked into maybe I looked at like 3 different textbooks of like intro physics textbooks from like university physics and college physics from Knight, and none of them really like clearly laid this out. But the power from torque is equal to torque times omega. And maybe I can help give you some, oh, is it freezing here? What's going on?